Welcome to the deep dive. Today, we're diving into the engine behind those really impressive large language models, LLMs, that you've probably heard so much about.
Definitely. We know they're amazing with text, right? Generating it, understanding it.
Yeah, sometimes it feels like they can almost reason, but we're going to look at something today that could make them, well, even more powerful.
Exactly. We've got some fascinating research here looking at how combining transformer models with graph-structured data could be a real game changer.
Graph structured data. So we're talking graph transformers.
That's the focus. We want to really unpack what graph transformers are and, crucially, how they might boost what current LLMs can do.
Okay, so think of this as your kind of quick guide to a really cutting edge piece of AI. Doesn't matter if you're super technical or just curious.
Right. We'll aim to keep it clear, avoid getting too bogged down in jargon. Hopefully you'll have a few aha moments.
Yeah, we'll connect some dots. So let's start at the beginning. What is a transformer model, in the context of these LLMs?
Okay, so at their core, modern LLMs are built on this thing called the transformer architecture. It's a massive leap for natural language processing.
A leap how? What did it change?
Well, it moved away from older methods, like RNNs or LSTMs, that process text word by word in sequence. The big innovation in transformers is something called self-attention.
Self-attention. That sounds like the LLM is sort of looking at a sentence and figuring out which words matter most to each other. Is that the gist?
That's a really good way to put it, yeah.
Yeah.
Self-attention lets the model look at all the words in a sequence, like simultaneously,
All at once.
all at once. And it figures out the relationships between them. So, the cat chased the mouse. It understands chased links, cat and mouse, and who did what to whom. It weighs the importance of every word against every other word.
Ah, so it's seeing the connections, not just the words in order. That makes sense why it'd be better for understanding meaning.
Precisely. Older methods really struggled with long sentences, connecting words far apart. Transformers, with self-attention, handle that much better.
So it's like seeing the whole landscape of the sentence at once.
You got it. And typically inside each layer of a transformer, you've got two main parts. This self-attention mechanism, actually, it's usually multi-head self-attention.
Multi-head, like it's looking for different kinds of relationships at the same time.
Kind of, yeah. Different heads can focus on different aspects like syntax or semantics. And then there's a feed-forward network, just a standard neural network part that processes the information from the attention layer.
Okay. Words in, attention finds connections, feed forward does more processing. Simple enough. But wait, if it looks at everything at once, how does it know the order? Cat chased mouse is different from mouse chased cat.
Ah, critical question. That's where positional encodings come in. These are like special mathematical tags added to the input for each word.
Tag.
Yeah, they give the model information about the position of the word in the sequence, first, second, third, and so on. So even though attention looks everywhere, the model still knows the original order.
Okay, clever. So, transformer architecture, self-attention for relationships, positional encodings for order. Got it. Now let's shift gears. Graph transformers. What are they? Why use this transformer idea on graphs? Graphs aren't sequences.
Right. Graph transformers, or GTs, are newer. They adapt those transformer principles, especially self-attention, to work with graph-structured data.
And when we say graphs, we mean networks, right? Nodes, edges, like social networks or knowledge bases.
Exactly that, not bar charts. Think interconnected data points. Now, we already had ways to work with graphs. Graph neural networks, GNNs, they're pretty good, but they have limitations.
Such as?
Well, a few things. One's called oversmoothing. As GNNs get deeper, the information from different nodes can kind of blend together too much, making them hard to distinguish.
Yeah, okay. They lose their uniqueness.
Sort of. Then there's oversquashing, where information from distant parts of the graph gets, well, squashed and lost as it tries to pass through bottlenecks. And maybe most importantly, GNNs often struggle to capture long-range dependencies. They're great locally, but miss the bigger picture sometimes.
So they see my immediate friends, maybe my friends' friends, but not the overall structure of the whole town's social network.
That's a perfect analogy. GTs were developed partly to tackle these issues. The idea is that self-attention, since it can look at any node pair, might be much better at modeling those global long-range relationships across the entire graph.
Because attention isn't restricted to just neighbors.
Potentially, yes. It can learn to attend to any node. And we are seeing GTs show success in various graph tasks already.
Okay, but that sounds like the core challenge, doesn't it? Adapting something built for linear text to this, like messy web of connections in a graph.
That is the fundamental challenge. How do you encode the graph's structure? Standard transformers use that linear order plus positional encoding. Graphs don't have one single order.
But they have structure, right? How nodes connect, the paths.
Exactly. Rich topological information. The key innovation in GTs is finding ways to represent this structure, what we call structural encoding. It's about feeding the graph's blueprint, not just the nodes and edges, into the transformer in a way it can understand.
Structural encoding. Teaching the transformer the language of graphs, not just sequences.
You've nailed it. And there's some really clever ways GTs do this. It's the key differentiator. It starts with how they handle the nodes, edges, and their features. But the crucial bit is integrating the topology.
How? What are these structural encodings like?
Well, there are a few main strategies. We can think about absolute positional encodings. These try to give each node a unique signature based on its overall position or role in the graph.
Like its address in the graph city.
Kind of, yeah. One powerful method is Laplacian eigenvectors, or LAFB. It uses some linear algebra based on the graph's connections to get embeddings that capture global structure. Models like Token GT use this.
Okay, that sounds quite mathematical. Any others?
Sure. There's random walk positional encoding, RWPE. This looks at where you're likely to end up if you just randomly wander around the graph, starting from a node. It captures more local diffusion patterns.
So how information might spread locally.
Right. And then simpler things like degree or centrality encoding used in a model called GraphFormer. It just uses how many connections a node has its degree as a basic feature, assuming more connected nodes are more important.
So different ways to assign an absolute identity based on global shape, local wandering, or just connection count. What about relative?
Good question. Relative positional encoding focuses on the relationship between pairs of nodes. The most common one is shortest path distance, SPD.
How many steps it takes to get from node A to node B?
Exactly. You calculate that distance, and then you use it to create a bias that's added directly to the attention score between those two nodes. GraphFormer does this. It tells the attention mechanism, hey, these two nodes are structurally close, maybe pay more attention, or these are far apart.
Ah, I see. So it's directly informing the attention based on structural proximity. Less about where am I and more about how close am I to you.
Precisely. And it goes beyond just encoding. GTs also use structure-aware attention mechanisms. The attention calculation itself is modified.
How so?
One way is that attention bias we just mentioned, adding something like SPD bias to the scores. Another is attention masking. You might literally lock attention between nodes that are too far apart, forcing it to focus locally, maybe just on direct neighbors or k-op neighbors.
So you can restrict its view if needed.
Yes. And you can also do edge feature incorporation. If the connections themselves have properties like friend, colleague, or a strength value, you can feed those edge features directly into the attention calculation. So it considers the type or strength of the connection, not just its existence.
Makes sense. Understand the who and the how of the connection.
Right. Then there are also tokenization strategies.
Yeah.
This is a bit different. Instead of modifying the transformer, you try to turn the graph into a sequence.
Like flattening the graph.
Sort of. The simplest is node tokenization. Just list the nodes as tokens. But you could do edge tokenization, where both nodes and edges become tokens in the sequence. Token GT does something like this. The hope is a standard-ish transformer can then process it.
Seems tricky to preserve all the structure that way, though.
It can be. It's an active area. And finally, people are combining approaches. Hybrid approaches use both GNNs and transformers together.
Best of both worlds.
That's the idea. Maybe use a GNN for local stuff and a transformer for global, or alternate layers like in Graph GPS. Lots of experimentation there.
Wow, okay. So a whole toolkit. Absolute encodings, relative encodings, tweaking attention, turning graphs into sequences, mixing models. But underneath it all, it's still stacked layers, self-attention feed-forward networks.
Fundamentally, yes. The architecture looks familiar, but the inputs are different. Graphs versus sequences. How structure is handled is different. Structural PE versus positional PE. The attention is often structure-aware, and the built-in assumptions are graph-specific.
Okay, that gives us a really good handle on graph transformers. Now, the big payoff question, how can these actually improve LLMs? What's the synergy?
Right. This is exciting. The motivation comes from where LLMs sometimes fall short and where graphs are strong. LLMs can, hallucinate facts.
Make stuff up, yeah.
Can struggle with complex, multi-step reasoning. And their knowledge is static based on when they were trained. Graphs, especially knowledge graphs, KGCs, offer structured, explicit relationships. They can be updated easily.
So graphs provide structured, up-to-date knowledge.
Exactly. The goal is to give LLMs access to that.
Yeah.
A major way is leveraging knowledge graphs. Think retrieval augmented generation, RAG, but using a KG.
Graph ray.
Basically, yeah.
Yeah.
When you ask the LLM something, it doesn't just rely on its internal training data. It can query a KG to find relevant, verified facts and relationships. This acts as contextual understanding and fact grounding.
So it checks the facts against a reliable, structured source.
Precisely. It makes answers more accurate, less prone to hallucination. KGs allow structured retrieval based on relationships, which is powerful. Plus, LLMs can become a natural language interface to KGs. You ask in English, the LLM figures out the graph query, gets the structured answer, and translates it back.
That would make KGs much more accessible.
Definitely. And it allows for dynamic knowledge integration, using the KG for up-to-date info. LLMs can even help build KGs by extracting structured data from text.
Okay, grounding facts, providing current info. What about reasoning? You said LLMs can struggle there?
Yes, and graphs can potentially help enormously with graph-based reasoning. Complex reasoning often involves relationships and steps perfect for a graph representation.
How does that work in practice?
We're seeing graph-guided reasoning frameworks, things like graph chain of thought, where the graph structure literally guides the LLM's reasoning steps, or agent systems, where agents collaborate based on graph connections.
Like a flowchart for the LLM's thoughts.
Kind of, yeah. Another approach is direct integration of graph learning modules. Models like Graph LLM use a graph transformer to process the relevant graph data first.
Okay.
Then, the GT generates a compact summary, like a structural prefix, which is fed into the LLM. This primes the LLM with the essential graph information.
Ah, so instead of feeding the LLM a long text description of the graph.
Exactly. You give it a condensed, structure-aware summary from the GT. Studies show this is much better for graph reasoning tasks, more accurate, more efficient. Simply turning the graph into text often makes the context too long, and the LLM wastes effort trying to reconstruct the structure itself.
Right, that makes sense. Let the GT handle the graph structure it's designed for.
Precisely. And research is also looking at weaving GT principles directly into LLM architectures for tasks involving text linked to graph models like GreaseLM, Patton, and others. The key point is, graphs offer structure that's often lost or inefficiently processed when just converted to text for an LLM.
This sounds incredibly promising. Grounded knowledge, better reasoning. But there have to be downsides, right? What are the catches with graph transformers?
Oh, absolutely. No free lunch here. A major one is scalability and computational complexity. That's standard self-attention. Its cost grows quadratically with the number of nodes, ON.
Meaning double the nodes, 4 times the work.
Roughly, yeah. For massive graphs, millions or billions of nodes, this becomes computationally prohibitive. It's much more expensive than typical GNNs, which often scale closer to linearly with the number of edges.
So GTs might see everything, but the cost of looking can be huge for big networks.
That's a big bottleneck. Yeah. Another issue is the potential loss of GNN inductive biases. GNNs are inherently biased towards local information. A node's neighbors matter most.
Which is often true in graphs, right?
Often, yes. GTs, especially with global attention, might lose that natural local focus. They can learn it, but they might need more data compared to a GNN for tasks where local patterns dominate. It's a trade-off.
Global view versus local efficiency. Okay, what else?
Well, there's the complexity in representing diverse graph structures. Designing those structural encodings we talked about. It's hard. You want something specific enough for one graph type, but general enough for others. Get it wrong, and performance suffers. Vanilla GTs without good encoding often don't do well.
Finding the one-size-fits-all structural language is tough.
Very. And then there are potential theoretical and practical reasoning limits. Some theories suggest standard transformers might struggle with certain graph problems requiring deep, complex reasoning. And there's often a gap between theoretical power and what can actually be learned practically, especially on huge, noisy graphs.
So even with attention, there might be fundamental limits to their graph reasoning.
It's an open question. Plus, you have other potential issues. Training very deep GTs can be tricky. Overfitting, maybe even over-smoothing again. Interpretability is hard. Why did it focus there? Handling dynamic graphs that change over time. Robustness to errors. It's a complex picture.
So the core tension is global reach versus cost and local focus.
I think that captures it well. The quality of the structural encodings and the inherent scaling limits of attention are really the key battlegrounds right now.
Okay, so powerful, definitely promising, but scaling and efficiency are major hurdles still being worked on.
Exactly. It's a super active research area. People are developing sparse attention mechanisms, graph sampling techniques, better hybrid models,
Yeah.
trying to get the benefits without the crippling cost.
This has been incredibly insightful, a real deep dive. So just to wrap up the main takeaway for everyone listening, graph transformers are a big deal for handling structured data,
For sure.
and they offer really exciting ways to potentially boost LLMs, giving them better access to structured knowledge and maybe even improving their reasoning.
That's the hope and the direction,
Yeah.
yes. The challenges, particularly scalability, are significant, but the pace of research is rapid. We're seeing constant innovation.
Absolutely. And maybe a final thought for you, the listener. Just consider how this shift from AI primarily processing linear text to understanding these rich, interconnected knowledge graphs, how that could fundamentally change AI's understanding of and interaction with our complex world.
Yeah, think about the applications.
Yeah.
Science, social networks, personalized medicine. The potential is vast.
Definitely food for thought. Thanks
Yeah.
for joining us on this deep dive.